first one was a general question about airflow pressure drop. Not a question on a specific problem, but I'd like to derive the equation of pressure drop changing as a square function of flow change in a fixed system for airflow applications. I know the affinity laws work, but can they always be applied for compressed air applications, HVAC applications, etc.? So good question. Let's just cover some background, maybe saying some things that you already know, but just to kind of, level set, and then we'll go from there. I don't know a derivation, but circling back to the affinity laws, if we start with the pump affinity laws, which I know your question is about the air side, but I just want to kind of establish that we're on the same page about this, at least this. And I'll jump right to the pressure, although it's usually presented, and it is in the reference handbook, as head. But suffice it to say that that's the same idea as pressure, is related to the ratio of the speed, the RPM, squared. And then we have a separate relationship that the speed, N2 to N1, is proportional to the volume flow rate, Q2 to Q1. So we can make that substitution into here and say that H2 over H1 is Q2 over Q1 squared. So nothing surprising there. It's just saying that the ratio of the pressure is the square of the ratio of the volume flow rate. So taking that same idea and extending that to the fan laws, if we search the reference handbook for fan affinity laws, I'll choose the one specifically for pressure again. And for some reason, they have it as P1 over P2, but you could certainly interchange those subscripts and make it analogous to this, but everything's just going to be upside down here. They have that as D1 to D2 times N1 to N2 squared times rho 1 to rho 2. So if we make the assumption that the diameter isn't changing, D1 equals D2, then this ratio equals 1. And if the density, rho 1 equals rho 2, then this ratio equals 1. And now by the same exact reasoning as before, the speed is linearly related to the volume flow rate. We can make a substitution. So we can say this now equals Q1 over Q2 quantity squared. So we have the same relationship on the air side as we would have for a fluid, a liquid. And this works as long as the density is held constant. That's the key. So I don't know if that's satisfying. It's not a derivation. I don't know that I know a derivation or that we need to, but those are my thoughts about that relationship and its applicability to PE type problems.
It comes up a lot in my profession. And I always see that, P1 over P2 is Q2 over Q1 squared. And that's just accepted. And I'm assuming that comes from like a Bernoulli equation application.
Yeah, I now that you've asked, it's kind of making me wish I had a deeper, more fundamental explanation for why that is. I've sort of just taken it as a given too. That the speed and the volume flow rate are linear. The pressure goes with the square of either of those, and then the power goes with the cube.
Good enough for me. I had said that in an email with my team, and my boss put into Darcy Weisbach equation and trying to use that in the application. And I was, making the point, let's not overcomplicate it. This function works for any fixed orifice or fixed K factor or whatever you want to call it. If you have a change in flow, the pressure drop's going to change the square root function. So cool.
Yeah.
Good for me, Dan. Thank you.
Cool. Awesome.